Hello everybody and welcome to this episode of the YoungWonks Podcast. Today we are talking about printed circuit board design. Sorry, I put the thing up a little bit late. Can someone just send a thing in the question thing saying that you can see it? The first thing that we are going to talk about is what are printed circuit boards, and then afterwards we'll get into the nitty-gritty of what is involved with designing them. My Firefox is acting up. I need to close that. Okay. First things first, what is a printed circuit board? You've definitely seen these things before. You just probably didn't know that they're called that. I will find a picture of a blank one. By the way, to be clear, there are two things that PCB stands for in technology. There's printed circuit board and polychlorinated biphenyl. The second one we're not concerned with because we're not chemical engineers, we're electrical engineers. But you may have heard of the second one in the context of being toxic and bad for the environment. PCBs look like this, or like this, or like this when they have no components on them. And if you want to see one with components on it, well, that's, I don't know, just like a computer motherboard here. So computer motherboards are one of the more visible PCBs that people interact with a lot because, you know, if you're building your own computer, you're going to buy one of these. Motherboard's just a really large PCB with connectors in certain places that follow the ATX standard usually. So what is a printed circuit board? It's actually not... Sometimes the term is used collectively to mean this entire thing, but technically speaking, the printed circuit board is the part underneath. This green or some other color, but most commonly green, thin fiberglass material with copper traces in it. And what it does is it makes the electrical interconnections between different components. So it seems simple enough. It's basically just, it's almost like a breadboard but fixed. It's electrical connections between different points that are fixed. Now, why are they so hard to design? First of all, if you've got all the components in different places, you can't cross connections, right? At least not in a single layer, because then they would be electrically connected to each other and you might not want that. So you have to route things, you have to route your connections so they don't hit each other unless you want them to. Also, printed circuit boards can have multiple layers if you need to have signals go, above and below each other. Also, if you get into the really complicated stuff, printed circuit boards actually can have antennas built into them, and they can have inductance or capacitance just in the traces. Because you are able to make any shape out of the copper on the board that you want, you can actually create an antenna, because an antenna is just a wire of a certain shape, right? So there's a lot of more advanced topics in PCB design that relate to actually using the PCB itself to accomplish some goal. Or if you've got really fast signals where the actual length of the trace that a signal is transmitted through matters, you might find that it's important to... sorry, is anyone actually watching right now? Because it says 0, but then... Just someone please send a thing in youngwonks.com/podcast questions if you're actually on here. Thanks. PCB design. There's a lot of stuff you can do with the actual properties of the design that changes its electrical characteristics. Also, and this is something you might encounter more often, there's the simple case of needing to do more than just interconnect. Suppose that you had a board that was designed to pass a lot of power. You would actually have to design some traces to be very thick so that the resistance, so that they can pass more current. So, let's talk about the design flow for making a PCB. I have a webcam in my backpack. I'll just get that hooked up. We are in the EE lab of my dorm right now, which is just a little room with some soldering and 3D printer stuff set up and an oscilloscope, but it's a nice place to record, so let's give me a second. I have to do all this live. You can see how this thing works. Add a new camera device. Okay. Camera. Okay. You should be able to see me now. transform. Okay. Hi. Here's the E-Lab. There's an analog oscilloscope. We've looked at it before. There's a power supply. And this is a little printed circuit board I designed quite a while ago now for controlling neopixels, LEDs. You can see on the back there's some text. I called it Duran Pi as a pun on Raspberry Pi. My dad helped me with the design. There's a very bad picture of a Duran on the back, and there's also a symbol that indicates the power is center positive. So you can see this PCB is actually purple. It's from people called Osh Park. They do hobbyist PCB manufacturing. It's got an ESP8266 microcontroller. That's this thing here. It's got 2 buttons. It's got power. It's got a connection to the LED strip. It's got a voltage regulator for the ESP8266. So let's actually look at this board's design. Now, I've never opened the design on this computer, so we will have some issues doing that. So I think I'm just going to show you the screenshots of the design rather than opening it in the actual software. So let's take a look at the design. It's all open source, so you could probably find it on my, I want to say Bitbucket, because back then I used Bitbucket, not GitHub. What do you guys want to see? We want to see home, projects, KiCad, and yes, we will talk about how you actually do the design. I'm watching, can see. Thank you very much. Okay, here we go. Web NeoPixel controller, PCB design.png. This is an image of the actual board layout. You can see components are represented just kind of as like outlines that have where the electrical connections are, where the pads and pins are. But you can see this is the same board. The yellow thing around the edge is the outline. When you send it to a PCB fab house, that will be routed out, so they cut it in that shape. Generally, you can make PCBs in any shape. You can even have slots or holes in the middle. There are certain limitations, but we can get into that later. So, this is the front view of the board. You can see stuff on the back. It looks reversed because it's on the back. Let's talk before we get any further about the different layers in a PCB. So I'm going to find you a diagram of a 2-layer PCB. And we will talk about... Okay, this is not everything I want to show you, but this is the thing. So, the simplest PCB is a 2-layer PCB. Technically, the simplest PCB is a 1-layer PCB, but generally, manufacturing services, the lowest they go to is 2. If you're making PCBs at home using a very involved process involving acid and a laser printer and a bunch of other complicated things that, given the current cost of hobbyist manufacturing, are no longer really worth it, then yes, 1-layer PCBs is probably what you're doing. But I digress. Top layer is copper, middle is FR4 usually, which is fiberglass, it's insulating, bottom is also copper. So that means that you have 2 layers in which you can have electrical signals. You've got the top copper layer and the bottom copper layer. Very often, because lots of things need to connect to ground, and also because you might have a lot of current being sunk through ground, the entire bottom layer is just grounded. It's called the ground plane. If you've got a PCB with more layers than this, like a 4-layer PCB, you might also have a power plane that brings in power. The substrate is what we call the green stuff in the middle. It's the actual fiberglass. There are other PCB substrates other than FR4, which is the most common kind of fiberglass. There's also flexible PCBs. Those look really cool, and for certain applications, they're useful. Here we go. You might have seen cables that are made like this. It's a really, it's an interesting new technology, and Osh Park actually has a new service making them. Now, next thing we need to notice here is plated through holes. So a via is a hole between layers of a PCB that's electrically conductive. So the way that works basically is they drill a hole through the PCB and then they copper plate the inside so it actually connects. So you can see this is there's a multi-layer board, and they're showing you that the vias actually make electrical connections between layers. So if you had stuff that was grounded, then you might use a via to connect it to the ground plane. Or if you have through-hole components, then you have to have a hole going through the board for the leads of the thing to go through. So in the actual manufacturing process, these holes get drilled out. If you look at this design, there are holes for a lot of the through-hole components. We should probably discuss what that means. Through-hole versus SMD. So through-hole components have leads that go through the board, and they tend to be an older technology because that's how electronics used to be made. SMD, or surface mount components, are just on top of the board. So if you look at a Raspberry Pi, you will see that the CPU is a surface mount component. Specifically, I think it's BGA, which means ball grid array, which basically means there's a whole bunch of contacts on the bottom of it and little balls of solder on each one, and they put it on there and heat it up and it melts it on. So if you look at the back of the Raspberry Pi, you will see that there are not like pins coming out of the CPU going all the way through the board. It just sits on top of the board. This obviously makes it hard to solder by hand because you can't really reach under the thing and you can't solder it from the back. But if you're machine manufacturing, it's actually much easier to do SMD stuff. And SMD components take up less space too, generally. However, if you look at the USB connectors, USB ports, you'll see those are through-hole. I want to find a picture of the back of the Raspberry Pi so that you can really see this. If you look at the back of the Raspberry Pi, you'll see that the USB, there are pins that come down, go all the way through the board. Now, there's a few reasons you do this. First of all, if the component you have is only available as through-hole, you have to do this. But also, it adds mechanical strength. So, for most components, it's not an issue. Nobody's going to be grabbing your CPU with pliers and trying to rip it off the board. But USB ports experience repeated stress when you plug them in and pull them out. So very often connectors like that are going to be through-hole for extra strength. Also, it might make it easier to sink a lot of current. It's really a decision you have to make based on how much space you have and whether you want to be assembling your PCB by hand. Places like Osh Park will manufacture the blank PCB, but they will not assemble it for you. PCB assembly is a more expensive service that you can get from other factories. But if you're just making like 5 PCBs for a home project and you only want to spend maybe 15 bucks, you're not going to have them assemble. You're going to be assembling them yourself. And so there is a design consideration that it's going to need to be fairly easy to solder. So if you actually open up the program we're going to use, I am watching Awesome Pattern. Awesome, 2 people are watching. Thank you. I'm not alone. This is going to go a bit longer than 20 minutes. You don't have to stay, but I mean, let's see how deep we can go. I have the first 3 weeks of an EE degree, so I'm definitely qualified to talk about PCB design. Anyways, the program that I use is called KiCad because it's open source, so it's free. KiCad's actually quite nice. Hobbyists used to use Eagle, which is from Autodesk, because there's a free version of it, but Eagle's kind of trash these days, and it has a lot of limitations on like how many layers you can do and how big the board can be and a bunch of other stuff in the free version. Now, KiCad, on the other hand, is really nice for an open source project. It can even generate a 3D model of your board so that if you are building an enclosure or something that mechanically works with the board, you can actually get a 3D model that has all the components on it, and you can visualize stuff and fit stuff together. That's a really nice advanced feature. Why is KiCad so good? Because CERN got some people to work on it. You may have heard of them. They run the Large Hadron Collider. Fun fact, they also invented the World Wide Web as a means of storing all of their data. So they're kind of big in science. You've probably seen pictures of what the Large Hadron Collider looks like. It's this enormous tunnel, and they bash protons into each other. And their PCB design has some, interesting requirements because they have some very fast signals, and so they put a lot of effort into making KiCad quite good, but it's still open source. So KiCad goes up to 32 layers of copper. It has some automatic routing so that you don't have to do everything yourself. It's really smart. Now, if you've got money to burn, the expensive tool used in industry is this thing, Altium. If you are a student, you can probably get a license for free for this, though, so yeah. I don't know how to use it yet, but I'm learning because the robotics team here uses it. It's apparently very nice, like in terms of usability. Like, it's hard to learn, but compared with Eagle, it's pro. But that's how it is with software that costs you like $10,000 a seat or something. Anyways, KiCad is really good, especially for hobbyist use. You may also see people using Fritzing for PCB design. Do not do this. Fritzing is something for designing stuff for breadboards. It is not something for designing PCBs. It has the capability to design PCBs, but they look really bad, and it's not a very advanced tool, and I would not honestly recommend that you start there. It's not really the same workflow as other things, and it produces PCBs that look kind of strange and are not routed very well. So, KiCad. There's a few steps in the PCB design process, but actually I suppose the first thing we should address is the other layers. There's a couple other layers you don't want to talk about. We've got your copper layers and you've got your substrate layers. Copper is conducting, substrate is not. But the other layers you have is silkscreen. So if you've noticed, most PCBs have writing on them. This writing is partially for humans to look at when they're assembling it, also partially because some pick-and-place machines actually look at the markings on the board for alignment. Also, if you need to write like a version number on every board you make. Also, if you need to indicate which way round components go, so you don't put them on backwards. There's a lot of reasons you need to label stuff on a PCB, and that's done with silkscreen, which is this white drawings and text on there. It can be other colors, it's just most commonly white. It's called silkscreen because they use silkscreen printing to actually put it on the PCB. So that's represented in the purple layer in this design here. The colors here are not the actual colors. The actual colors of things depend on what your manufacturer is doing. The colors shown here are just used to differentiate between different layers. For example, red is front copper layer, purple is back silkscreen, blue is front silkscreen, etc. So, the basic design flow of making a PCB is you draw your schematic first, which is all the components and their electrical connections, paying no mind to characteristics like how thick a wire is or where a component is. You don't deal with that at the start. You're just, this is my circuit. You design a circuit. Then you export a net list, which is a thing that says these are my components and this is how they're connected together. And you import that into the layout editor. And the layout editor lets you actually place components in different places and then actually route the exact copper traces that go between them. So let's do this. New project. I'm going to create a new project. I'm going to put it, I don't know, under downloads, example, PCB, save. Okay, this is my new project. KiCad is ready. You go to here first, schematic layout editor. So this is just a blank schematic. If you wanted to make like a hat for your Raspberry Pi, there are template projects you can use where all of the basic stuff you need is already set up, and then you just add your own circuit for the specific parts of the hat that you're developing. But I digress. Let's make some electronics. I just zoomed in a bit there. Okay. So, this tool lets you place symbols. So, what do we want to do? Let's make a PCB that, I don't know, has an LED on it and a switch, and then has some pins that connect it to a battery. We're just doing an example. So, your symbol library is a library of every component you can use. If you need specific components that aren't in the default symbol library, because the default symbol library is pretty generic and not great, you can download symbol files from the manufacturers. Those will usually be provided somewhere. If not, you have to write the symbol file yourself by drawing out exactly where the different parts of the thing are, and it's tricky. Anyways, we're going to search for an LED. This is just like a generic LED. I'm going to place it at some location, doesn't matter where. Next thing I want is a resistor, because LEDs need a resistor, right? Resistor. Next component I need is a switch. I'm using the sort of generic components that KiCad comes with. If you're actually making your own board with components from a specific manufacturer, you're probably not going to want to use the generic stuff. Although you can always use generic ones, but then assign specific footprints from a certain manufacturer later. Anyways, I just want to switch. I just want to switch. What kind of switches do we have? Hang on. These aren't switches. Button. Actually, yeah, button's probably what I want. Rotary switch. I don't want a rotary switch. I want a regular switch. Ah, there we go. That's just a nice push button switch. Okay. By the way, pressing R rotates a component. There's no electrical impact of that. It's just if you want stuff to look nice and how you arrange it. So, last component we probably want is the actual header. What I want is a board that has an LED on it, a resistor, and a button, and then some external connection to power. You hook up power to it, and then when you press the button, the LED lights up. It's just an example. This is not a particularly useful button, but there you go. Pin header. Pin header. Connectors. So this thing lets you search. That's how I'm getting to things so quickly, by the way. I'm not that fast at scrolling. So there's a lot of complicated connectors here, like the connector to plug a micro SD card in, but we don't want that. I just want a dead simple connector. Here we go. Connector generic. This is not what I want. I want something that just has one row and 2 pins. That's female. I actually want male. There we go. So this is just a header with 2 pins on it. You know, like the headers on a Raspberry Pi, but less pins. So now we've placed the components that we actually want. We can zoom in. The next thing we have to do is wire them up. So we click on this tool over here, which is the wire tool, and we just click where we want to place wires. Click, move, click, click, move, click, click, move, click. So is this correct? We're going to say that power comes in on one of these and flows in through 2 and then flows out. Now, if you wanted to actually move something, you press M and then you can move it. And now I need to wire this up. Hang on. I've messed this up a little bit because I moved it afterwards. Delete junction. Delete wire. Okay, there we go. So, if you wanted to actually indicate to KiCad which thing is power and which is ground, there are special symbols we can add. We're not doing that right now. So, Control S to save. Now, the first thing we need to do here actually is assign numbers to everything. You notice there's a question mark because we haven't assigned numbers to the components. Every component has a number and a letter, like D1 or R1. These allow you to identify stuff so that when you're putting the board together, you know, things are labeled with what they are and you can put them together without too much guesswork. So, let's do that. Number assignment. Hang on. Annotate. Okay. Annotate. So, annotate schematic just sets the numbers automatically. We only have one of each thing here, so there's only ones, but now there's no longer question marks. That's just a step you have to do. It doesn't do it automatically in case you want to assign numbers based on your own scheme. You can you can also edit them like directly if you had the inclination. We don't have the inclination. Calling everything just 1, 1, 1 is fine here. So, next thing we got to do is assign PCB footprints. So this is the part we have to talk a bit more about. Hang on. No questions yet. These schematic symbols don't have actual like shapes. Like an LED on a PCB is probably going to be 2 holes in the PCB, with copper, so basically two vias next to each other. One of them is plus, one of them is minus. This schematic symbol has no association with that until we give it an association with that. And obviously, different LEDs have different footprints on the board, so we need to assign a specific footprint to each schematic symbol based on what exact component we're using. Assign PCB footprints. Give it a sec. It's kind of slow because it's like a vast number of footprints in the library and it's copying it in. Give it some time. So, to reiterate, a schematic component doesn't have a footprint. It's just a schematic component. If you want to turn it into something like what we have for the button or the connector here, an actual shape on the board, then you assign it a footprint. So each footprint first has the locations of holes that need to be drilled. It's also got where there should be copper and where there should not be copper. It's also got sometimes an outline of how much space on the board the component actually takes up. For example, my buttons on this board are very large, and so you can see there's a circle around where the button's going to be, and we can't put any other components within that circle, because then the button would be on top of them. Some footprints also have silkscreen in them so that there's like a label that's attached to it, although that's usually, there's different ways of doing it. So you can also add silkscreen yourself, but they also sometimes have text that shows up like in the editor but doesn't show up when you actually make the thing. For example, you see that this resistor over here says 10K under it. I believe that's actually not from the footprint, that's from KiCad, but when you actually have the PCB made, that text doesn't show up. What shows up is this silkscreen which says R2. So reading a layout like this requires some understanding of what colors mean what. But footprint assignment's fairly easy. Basically, you have your little table here with your components, and then you have footprints, and you tell it, oh, this footprint goes to this thing. You can use this thing to filter the footprints to search them. So the first thing we want is an LED. So I'm going to set the footprint filtering to name or pattern, which means that I'm searching by typing into this box, and I'm going to type in LED. So you're going to see a whole bunch of things that match LED. I just want a footprint for, like, I don't know, a normal LED, like just some LED. Here we go, a 3mm LED through hole. THT means through hole. Yeah, that seems good. Double click it and it assigns it. Now that has a footprint. Next thing is our header. I just want a generic header that's 1x2. So let's try to find one. 1x2, I want vertical pins. There's no real reason I want either, but let's just say I want vertical pins. So let's find one that's named that way. And I want the pitch to be, hang on. Here we go. Headers, you want 1x2 actually. Alright, 1x2 vertical pin header, 1mm pitch. That's a bit weird pitch. Let's see if we can find pitch, pitch is the distance between them, by the way. I believe standard pitch is, hang on, let me check. The distance between the headers, you know on Raspberry Pis the headers are spaced a certain amount, and most things follow that spacing, like Arduinos have it as well. Pretty much anything that has headers that humans interact with uses, I believe, 2.54mm spacing. So let's try to find 2.54mm. Yeah, there we go. 1x2 vertical 2.5mm assigned. Okay, next thing is the resistor. I want a through-hole resistor. I don't want a surface mount or SMD resistor because it's going to be really hard to actually, like... Oh, interesting. Why is it not finding resistors? Filter by library. Okay, resistor through-hole library. Okay, I want a single through-hole resistor of, I don't know, relatively standard size. I don't want a resistor array. Looking at these namings is very confusing, so you may need to like place one and then see what it looks like. See, if you right-click, you can view the footprint. You see, this is the footprint for that resistor. That looks too small. I think that's for a smaller resistor than we probably want to use, like, physically. The resistors you guys are used to, I believe, are 5mm, but... Oh, hang on, that's for vertical. You want horizontal. That looks reasonable. Again, if you're actually making a board that, you know, has some specific components that you already know you want to use, you will have certain specific footprints. Last thing is our switch. Let's find the library for switches. Or buttons or whatever. Here we go. Buttons. I'm doing everything through hole so that it's easy to solder if we ever actually manufacture the board. Push button switch. I mean, yeah. Awesome. Apply, save schematic, and continue. Okay. So now all of these actually have footprints associated with them, which means that we're one step closer to actually designing a board. So next thing we do is go generate netlist. Generate. Save. So the netlist is the components and all their connections between them, and that's the thing that we use to actually do the layout. You notice that the netlist can be generated in formats that can be read by other programs as well. For example, if you wanted to run some simulations, you could actually export the netlist directly from here to there and then run the simulation. It's really cool. You actually don't need to do that these days because KiCad actually integrates, I think, ngSpice Simulator. Now, there's the other thing you should definitely run, which is the electrical rules checker. Sometimes also called DRC. This thing checks your mistakes. Now, usually you're going to have some rules set up that set things like, you know, power and ground can't be shorted together or whatever, although that's usually something you check yourself. Design rule check is something you run on the layout of the PCB, and it checks things like, oh, you know, is the clearance around this thing large enough that it won't accidentally short out? Is there enough thermal clearance? Actually, that's a complicated topic, but you can verify that certain aspects of your design will not have issues, and this can be done automatically. It is very important that you set up good design rules that make sense for your project. If you're making a little low voltage PCB like a hat for a Raspberry Pi, you know, you can get away with this not being a huge issue. But if you're making something that's got high voltage, you know, you need to have rules so that the program will stop you putting, you know, a 0-volt trace next to a 500-volt trace. You could have arcing. There's danger. Anyways, that's my spiel. Let's design the board. So we now press this thing here, run PCB new, which is the layout tool. Yeah, enable graphics acceleration. Okay. So you see this is just a blank layout now, but if you press load netlist and then select the netlist file that we just created, and then press update PCB, and then close it, it brings in all of our stuff. I'm going to drop all of it there. For some reason that resistor is enormous. I guess I chose the wrong footprint there. But hey, maybe there's a really high power LED. So I just zoomed in a whole bunch. I'm going to zoom in a whole bunch more. Okay, or actually, sorry, zoom out. So you notice that it doesn't do any like electrical connections automatically, but it does have these white lines called rat lines, and that's the electrical connection. So if we you know, start moving things around, Hang on, how do you... Oh, you can press G to grab something and move it, I believe, but something's wrong here. It's like selecting all of them. Give me a second. There we go. G... Nope. Yeah, there you go. Okay, you just drag. So you click and then drag to move stuff. So the first thing you have to decide, the very first thing you have to decide, is where physically are the components going to be. And this is a decision that will change as you start thinking about your routing. And you can also change the orientation of components. For example, you see these rat lines, these white lines that represent the electrical connections we need to make. You see they're crossed here. That's not good. So let's click on this component, press R to rotate it. So now they're not as crossed. Let's rotate that as well. Okay, that's better. Now we don't have things crossed, which means that when we actually, draw the traces won't be crossed. Let's also rotate that so that it's like that, and rotate that so that it's like that. Okay, now we're getting somewhere. Now the next thing we have to do is actually say, well, where are our electrical connections? There, where the rat lines are, we need to route them. So we click on this thing, which lets you draw traces, which are the actual strips of copper in the board that make electrical connections. So we're going to draw our trace from here to here. I'm going to draw a trace from here to here. I'm going to draw a trace from here to here to here. Now, because these are just like a little board that powers an LED on and off, there's absolutely no reason that the shape of the trace or the length of the traces matter. So if you're making some board with like radio frequency stuff, that's when it starts to matter, but we don't care here. Alright, save. Now, that's our layout done, but we need to do the actual outline of the board. By the way, if you wanted like a piece of copper that's not like a trace, you can also draw polygons. For example, if you needed something that has a lot of power going through it, you might have a plane that's just solid copper. Those are often called a pour. We don't need a ground plane here because this is such a simple circuit, but you can do that. Now, you can also do vias. If we had multiple layers, for example, maybe I have a trace that's, I don't know, doing this. If you press V when you're doing a trace, it makes a via. And if you click, it goes through to the other side of the board. So you see the front side of the board copper is drawn in red, and the back side is green, and then the vias are the little white circles. I will show you what that looks like. But the next thing we need to do is actually set an outline for the board, because otherwise this board, we don't know how big it is. I believe graphic polygon is actually the tool we use here. Sorry, if you're doing a copper pour, you would use add filled zones. So I think what we can do is just draw the outline of the board like so. Oops, okay. Oh, sorry, okay. There are many, many layers in a PCB, and different layers mean different things to the manufacturer. The layer we're in now is, hang on, what layer are we in now? We're in the f.cu layer, or at least the traces are in the f.cu layer. F.cu means front copper, so it's the copper trace on the front of the board. If you want to set the cutting of the board, like the shape of the board, then I believe that you set it under edge.cuts. There we go. These specific names mean something to the manufacturer. The very last step in PCB design is generating Gerber files, which are a standardized file format that you send to a manufacturer that tells them how to make stuff. These layer names mean something. For example, you can actually set where the glue is using the adhesive layer. You can edit the silkscreen layer to change the silkscreen. In our case, we want to change the cutting, so we're going to put a polygon in the cut layer. Or actually, we're going to do it with lines. Okay. This is a ridiculously large board for what it is, but that's how it be sometimes. Okay, so now we've set an outline of the board in the cuts layer. I'm going to go to the front f.silkscreen layer, and I'm going to add a version number. Because whenever you make a PCB, you always write the PCB version in the silkscreen. Because otherwise, when you have multiple versions, you don't know which one is which, and then it's confusing for the next person to work on the project. So we're going to say that this is LED board V 0.0.1. Also remember that stuff on the back, I think, should be mirrored, because I don't remember if KiCad does this automatically, but remember, if something's not mirrored, then if you look at it from the back, it may be wrong. Anyways, let's now use the really cool feature of KiCad and go View 3D. This generates a 3D model of our board. So you can see that the default KiCad footprints actually have 3D models associated with them. So this is a 3D visualization of our board. So as you can see, we've got our header where power comes in. You can see there's white where there's silkscreen labeling things. You can see our resistor, our LED, our button. You can see the traces. You can see that because these things are through holes, there are holes that are copper plated that go all the way through the other side of the board. And the stuff sticks out on this side. That's where you would solder it. And you can see the silkscreen. This is a really nice feature. I believe you can even export the 3D model and then use it like as part of your, you could send it to your Mech-E team. Anyways, I want to show you guys what a via would look like. So let's just make a random via that doesn't do anything. We're going to go back to our f.cu layer. We're going to create a wire. We're going to just start the trace here. We're going to click. We're going to press V for via. That takes, Okay, you've got trace starting here. We go across, press V for via, which gets us to the others. Nope, doesn't want to do it. Hang on. Okay, press V for via, then click to place it. Now it's green, which means we're actually on the back of the board. So this via went through the board. I'm just not connecting to anything. Yeah. Is it going to let me do that? No. KiCad kind of enforces that you have to connect to things that make sense. So I just made a connection that doesn't do anything. It just goes from here back to here by going through the back of the board. I did this because I want to show you what vias look like. So if you go back to your 3D view, you'll see that the via is actually a little hole in the board, and it's copper plated on the inside. And if you look on the back, it goes through there, and then there's a trace on the back that connects to there. Pretty neat. Vias are very useful if you've got more complex circuits going on. Oh, you can also do nice renderings of the view with the ray tracer. See, that looks a little bit more visually accurate. Anyways, getting rid of that. Now, this has been dragging on quite long, but this is quite a good intro, I think, in terms of, you could, with this amount of knowledge, you could design at least a simple PCB yourself, I hope. Last things. The last thing you do is export Gerbers. You go export. Oh, hang on, where is it? The Gerbers are the files you actually send to the, design rule check. Run DRC. So you see the design rule check doesn't say there's any problems, but, if I had put something too close to a pad or something, then maybe it would say there was a problem. Last thing you do is generate Gerbers. How do we generate Gerbers? It's been a while. Oh, another really useful trick with this is to actually print it out, on paper. Take this layout and print it out, then get all your components and put them on that printed out piece of paper to check that they physically line up with the footprints and you got it all correct. Anyways, tools, inspect, route, place. Fabrication outputs. Okay, you go to File, Fabrication outputs, I believe. Then you have to generate, well, actually a number of things. A BOM file is bill of materials. That's the list of components. You also need to generate your Gerbers. Hang on. To generate Gerbers, you actually go to the plot thing, not export. Export is if you want to go into another program. So you go File, Plot, and it's got a whole bunch of complicated settings here, like which layers you want included in the thing. I don't think we're including the adhesive layers because we don't really want to control where the manufacturer puts glue. We're just going to have them put glue between the layers everywhere. We're plotting Gerbers, which is our file format used to tell a manufacturer what to do. There's a lot of settings you can do here. You can include or not include different things. You can have silk screen. Oh, last thing, solder mask. That's another layer that's included. Solder mask is a material that repels molten solder. So you put it like around stuff so that when the solder melts, the solder only goes in the places that it should. If you ever did a crayon resist in elementary school, you might be familiar with this concept that like if you like draw with crayons on paper and then try to watercolor over it, the water is repelled by the wax in the crayons. It's like that. It's actually really useful because then these kind of the surface tension of the molten solder pulls components into place. So if you look at like a GIF of the reflow process, which is how a board is soldered by heating it up, you'll see sometimes the components actually kind of line themselves up. There you go. You see how that resistor, I think that's resistor, might be capacitor, was actually off angle at the start, but as the stuff melts, it actually pulls it into place, and all the solder that was on the green parts, which is the solder mask, actually gets pulled in because the solder mask repels it. So it's important to get your solder mask right. Usually the footprints have it automatically, but, you know, make sure. All right, plot. Great, we generated our Gerbers. I think you have to generate drill files as well. I can't remember, actually. Example PCB. Generate drill file, close, close. Now, if you want to get this manufactured, you'd go to Osh Park. They actually let you give them like KiCad files directly, but we're going to do it using the Gerbers because that's sort of the generic manufacturing way to do it. So give me a second. I'm just going to copy all of my Gerbers in and all of my drill files. I should have just made this folder earlier. The actual KiCad files, you can give them directly, but I would actually recommend that you do the Gerbers because it's, you don't know that they'll read the KiCad file format completely correctly, although they do show you a preview so you can kind of check that they got it right. All right, I'm going to zip my Gerbers folder into gerbers.zip. Hang on. How do you do this? Gerbers.zip Gerbers? There we go. So now I've got a little zip archive of all my Gerbers. Pretty much any manufacturer will accept that. Uploading design, processing. Awesome. This is a 2-layer board of this size. 3 boards will cost me $12. I mean, given how inefficient this board is, you know, we could have made this like a lot cheaper. They charge you by the square inch usually, and a 2-layer board is less expensive than a 4-layer board. So right now, you know, I could put in my credit card number and have this board in a couple weeks, or if I paid a lot of money, a couple days. I'm not going to do that because it's kind of a stupid board. But you can see that the process to have your own PCB made is quite painless these days. And, you know, I recommend you try it as a way to make the electronics in your projects a bit more professional. All right, let me check one more time if there's any more questions. Nothing. All right, thank you all for coming. See ya.